Welcome back, everyone, to the next talk in our application track. Please join me in welcoming Gianmario from BARCLAYS.
This slide, advanced Spark users may be looking at this and saying, wait a second, you're doing a group.
All right, so I'm Gianmario. I work as a data scientist at BARCLAYS in London. And today, I want to present the first Spark application that has been deployed in production at BARCLAYS. And the title is Hundreds of Queries in the Time of One, because that is the main characteristic of an insight engine that we built. Before to actually go into details, let me give you some background. BARCLAYS is a bank, and in UK, in that scope of this presentation, even though the bank is worldwide, we only focus on the UK. And in UK, we got like 1 million of business customers, of which 95% of them, they are small businesses, like small shops. Most all of them, they accept debit card transactions as a payment. And as you can imagine, there's a huge potential for business analytics here. But the problem is that businesses, those small shops, they cannot really harness their own data and compare their performance with their competitors. And that is because, first of all, they don't have enough money to invest in that. They lack proper IT infrastructures. They don't have analytics expertise. And also, that is important over here, even though they can manage to install a BI system, then they won't be able to actually get any information about the market, what the competitors are doing. So what we decided to do at BARCLAYS is building an insights engine that we provide as a free service for all the business customers, where what this engine does is calculating a bunch of business key performance indicators by combining hundreds of different queries. And those queries, what they do, they compare what are your performance with your similar businesses in your same area, in your same location, in your same industry. And by doing that, then it computes some insights that then are ranked based on some relevance score, and filter based on, we always make sure that we only show things that preserve the privacy. And everything is then presented in this natural language form in the web UI, where, for example, you can see this is your business, what your business is performing, and that's like your similar business in your area, for example. Let me give you a specific example of what an insight is. We're going to use that example for the rest of the presentation. This year, your business spent £1,000 on electricity, and other hairdressing businesses in Blackpool spend an average of £1,200 on electricity. So that is one type of insight. For example, very simple, very basic. We're going to use that one as example. What is important is that each insight type is defined by a triple of time, industry, and location combination. So if you are located in Blackpool and you're doing hairdressing, then that is what characterizes your specific business. Hello? All right, so in order to build this insights engine, we had to face a few challenges, okay? First of all, we wanted to use Spark. We decided to use Spark mainly because we wanted to avoid doing multiple operations on the same data set. So we want to have a very optimized in-memory execution plan. And that was the main reason why we decided to go for Spark. But we couldn't just use Spark SQL or data frame here, because we also wanted to have, we built that in a very agile way. So we want to have some statically typed language. And we also wanted to specify the logic of the whole system by combining, by composing different functions. So that was built in a pure functional programming way. And those are the main reason why we had no other choice, and we were very happy to build the insight engine in Scala. And that was not just the best solution, that was the only solution for that problem, because Scala is native to the framework and offers a bunch of flexibility. It's the best trade-off if you actually building a data product. Now, I mean, today, in the current technology we have available. And please pay attention that none of the above would be feasible in any of the relational database systems. So another reason why Scala is very cool, and if you don't know, the word Scala comes probably because you can, from this main feature where you can adapt to any domain-specific, in any domain you're building an application, in Scala you can always define your own domain-specific language. So by specifying your queries in the form of a DSL, what you get is an elegant way where it just has a few lines, very concise. It's natural because it follows the English way of speaking, and it is compiled. That means you can spot errors at compile time rather than runtime. So these are how we specify the insert types. And another important concept when you're doing, especially when you do a lot of transformation and aggregations, and you want to do everything in a functional way, you will probably end up doing a lot of monoids. Well, commutative monoids is an algebraic structure which is made of a triple of 3 elements. You got a type, you got a binary operator, which takes 2 elements of the same type and merge those 2 elements into a single element. And then you got a 0 element, which is like, if I apply this operator to the 0 element, you always get the same result. You get the first element. It's like it doesn't change anything. Let me give you some example. If you're doing a sum, like the simplest monoid that exists, the sum is gonna be defined on integers. The operator is the sum, and the 0 element is 0. If you're doing something like distinct or like multiplication, you're gonna see that the 0 operator is 1. If you're doing a distinct over a set, you're gonna have like a set empty, and you're gonna use the union as operator for your monoid. What is important are those 2 properties over here, because a commutative monoid is associative and commutative. And having those 2 properties means that you can parallelize any composition, any aggregation, it can happen in a hierarchical way in parallel. That is the example, how you would aggregate, like, say you start with your partitions, data in your partitions, and then you do hierarchical multiple steps of aggregation until you get to the final stage. That is the most scalable way to aggregate data. In our example, our monoid is that I'm going to use for this energy spending example. Is going to be a simple tuple of a count of transactions and sum of amounts. Now, I'll show you how we define the insight types through the DSL. I'll show you what the atomic part of our computations are. Now, that is where the optimization happens in the insight engine. We take the set of all the queries we want to compute, and because now is compiled, the queries you want to compute, we can inspect inside the code, in the Scala code, we can inspect it, and we can extract the minimum number of informative parts to compute. So many of the queries, we're going to share some intermediate results, and we never want to compute the same things twice. So we extract the list of all the parts that we want to compute, and in our particular example is, if you compute the spending growth of energy, like electricity, you're going to see that each part is composed by some filters. For example, outgoing transaction of energy. That means spending of electricity. And then we're going to have the list of monoids that we want to compute, which in our case is just the count and the sum of amount. And in order to compute the final insight, we need 4 parts, because we want to know how this business is performing in the current time slot. We want to know how this business is performing in the previous time slot. And then we want to do the same for our competitors, so then we can compare the growth. Once we have extracted what is the optimized set of parts, the minimum set of parts that we need in order to derive the insights, now here's where the action happens. We're gonna fill a sort of all-up cube here based on 3 dimensions. We got industry, we got time, and we got location. And each of those dimensions, they are defined at different granularities. So as industry, you're going to have like the subsegment and the higher group. It could be like hairdressing, for example. You have time, and you got location where you got different granularities over the whole country. Each cell of that cube is going to contain all of the monoids for each part that we extracted in the previous step. Okay. For example, if we take like the cell where the time is month, the industry is hairdressing, and Blackpool, we're going to have like, those are like the monoids that we wanted to compute in order to get the final insight. So once we fill this cube, now all we have to do is just take all the parts, take those 4 parts, okay, have a collate function that is able to combine all of those parts into a final insight. For example, we want to compare the growth, okay, my business growth in electricity spending, my competitor's growth in electricity spending, and then we apply this growth function, and we get the insight, which tells you, oh, this year you spend £1,000, and your competitor spent 1,200. Now that you know all the components of how the insight engine optimization work, let's go back to the DSL. That is where we specify everything in Scala code. So we use a lot of traits, case classes, and case objects to make our queries compiled here. So we need to create a granularity object where we specify what the comparison level is, where big code is the segment, nuts2 is the level of granularity for the location. We have to specify the time window, got year, for example. And here, we got all the parts. So that part is filter all the transactions, outgoing transactions, where of the previous time slot, where it's competitor, so it's not me doing the transaction, but it's my competitor, and this spending is about electricity. And then compute those monoids. Sum the amount, count the number of transactions, and count how many unique competitors we have. The reason why we need this extra third monoid over here is because we're reusing that for making sure that it's privacy complaint when we present the final insight. And then that is our collate function. Compute the average amount, and then compute the growth, my average, and my competitor average. Now, just to give you some numbers, as you can imagine also, this is a big corporation, big bank. So what we built the final production code. We hand over the jar to some engineers and then run tests and then deploy in production. So from our side, when we deploy that, those are the tests that we did. And just with 2 years worth of data, and just for a small set of 300,000 businesses, let's have an estimation. Let's have an estimation of, in order to compute like the final 66 insight that we were interested in our test, that is the upper bound. So essentially, we had 9 insight types, 9 queries. Each query was made of 4 subqueries, which are the 4 parts. And each part must be computed for each combination of granularity, which is like 36. So that explodes to 1,300 queries. And if you add more dimensions here, or if you just add more queries you want to compute, that one just explodes. And if you try to do that in a sequence of queries, it's never going to finish. It's never going to scale. So in our case, after done all of those queries, and after filtered by privacy and did some ranking of relevance, because we don't want to show all of those thousands of insights. We only want to show the relevant ones. After that, we end up to 66. And all of these run with just 30 minutes in a very low performance cluster, like 6 nodes, nothing. and then it just managed to run in 30 minutes. And when we tried to do that in Hive, it took like, our estimation is like in Hive, that would have taken 500 times more to run all of those sequence of queries. And probably in Teradata we tried, but then we just gave up because it would never return. So just to summarize, what this insight engine is an analytical engine where it takes a bunch of queries and combine them into a single execution plan. And what is very cool is, first of all, the use of composable monoids. This definition of this elegant DSL for define the queries. The inspection of the query in order to find duplicate structure and applying an upfront minimization so that you never compute same part twice. And all of that is then, it goes through our privacy and relevance engine and is presented in this web UI. So if you're interested on knowing more about how to apply functional programming and Scala and Spark to build data science application, there are a few links you might be interested. I also would like to, if you're interested on how to apply Agile in that context, also would like to promote. There's a community of data scientists who are doing this great initiative, is the Manifesto. It's essentially what they're trying to do, they're trying to extend what is the Agile Manifesto for software development and how to apply the scientific method together to actually define some principles so that can guide the development for data science applications. So if you're interested, please contribute to that. And that's the end of my talk. Is there any open to questions? We got like 8 minutes.
First of all, functional programming part was delightful. Thank you for that. Besides that, do you plan to do something similar for consumer part of your banking? I mean, I would like to compare my family with other similar families in terms of spending on gas, etc., etc.
So that was the first version of the insight engine we deployed in production. That is for my business data. We already working on the my customer data, where we are doing the same, but we're gonna offer that one to the personal banking accounts. So you will be able to do that in a few months if you bank with Barclays. That is the only bank in the world that offers that.
Hi, so a quick question here. As far as I understood the previous slide, you were exploding all the dimensions in your cube, right? So you're materializing this 1,296 essentially, go to the right twice?
Yep.
So you are, all the dimensions you have there, you're materializing all the queries and all that, right? So I'm just wondering, instead of doing that, would it make sense for some of the metrics to be computed on the fly instead of materializing them? So some of the insights, for example, all the users are seeing all the insights, or there are some suggestions or some insights that nobody will ever see. So would you compute those on the fly? That's my question.
So sorry, can you just repeat the question?
The question is, I understand you materialize all those numbers. Would it make sense to not to do that and materialize some of them on the fly?
Yeah, the reason why I need to do that is because I was not enough time to go into details of how the relevance engine work. So essentially, for each insight type, for each type of insight, we do compute it at any level and in any combination of those dimensions. And then what the relevance engine does is filtering out only the interesting stuff. So in order to know what is boring and what is interesting, you have to compute for any combinations. Because I give you an example. You are a hairdresser in Camden in London, and then everyone in your area, they do perform very similar to you. So if we're trying to do the insight, it's going to be very boring. So like, oh, you go like 0.01% more than your competitors. It tells you nothing. But if we maybe change the level of granularity and we go to, I don't know, like South England region, then your business is going very well. So that is what you are interested in, and we only want to present you with what is important for you. So in order to do that, we need to do all the combination, then we do the selection. Yeah. This one.
First of all, thank you for your talk. I think automatic insight generation is a very interesting topic. Question here would be, you're showing the difference to the mean, but sometimes the standard deviation could be much bigger than actually the difference that you're seeing. So maybe the insights can be a bit misleading. So I'm wondering if you also considered looking at median or percentiles and this kind of things, and would it be possible to apply that with your engine as well?
So I just used the simple example for the slides, but the concept of monoids can be extended, and sometimes his definition that is it has to be deterministic. If you want, there's one challenge which is about how can you create a monoid to compute a median. And you can find that it's open source. In the last slide, in the link, there is a GitHub page where there's the code, where if you want, you can apply to this challenge. It's like, how can you implement a monoid for computing the median? And there are a lot of probabilistic methods where you can estimate the median with a given degree of error. So the whole concept is that if you manage to take any computation, any aggregation you want to do, could be the median, could be, I don't know, distinct set, whatever statistics you want to compute, you can always break it down into a few, like a tuple of single monoids that you want to compute, and then you're gonna derive your median from them. That's what, yeah. So we, in our insight engine, we did some distinct count bounds using hash set, for example. If you go to that GitHub page, you're gonna find a lot of example of how to compute like the median for aggregating medians using the monoid fashion. So you can do a lot of stuff, a lot of cool stuff, and everything is functional. That is the key point here.
Hi, thanks for the talk. This is more of a businessy kind of question. So if you give insight back to a company and they're doing worse than someone in their area, do you just give them a number or do you give them further insight?
That is how it's presented. So you're gonna see something like that. Like every day you log in your web page, you have a shop, and every day we're gonna tell you something about your business. So today we're gonna tell you that you're spending too much in electricity, you see? It's like your average should be 1,600, why are you spending more than that? You shouldn't. And sometimes we tell you stuff like, how much was your growth in that trimester with respect to last year? Sometimes we answer questions like, what's your market share? What's the wallet share? Like in your areas, we see where people spend, and we can tell you, oh, you have the 5% share of all the hairdressing of your area. We know all of that because your competitors are our customers, your clients are our customers. So we do have a global view of everyone, but obviously everything is presented in such a way that you will never be able to derive what information of your particular competitor, because we always present in an aggregated way, so that there's no way to actually understand, the single competitor what is performing.
Okay, thanks.
How do you account for what you don't know, as in?
Sorry, how do you account for?
What you don't know, like what's non-Barclays customers? Do you kind of make an estimate of, we ourselves have this much market share, et cetera,
Yeah.
and projections?
So, because every insight we compute, so Barclays has like 30% share of the POS device. So you go like 30% of all the transactions in UK. So it's a good, it's a good portion of the data. So, but obviously if there's any bias, like the data, let's say we only have a 30% sample of the whole transactional data set. As long as we know that represents the same distribution, then we know that the insights are meaningful. In any data science problem, you're always going to have that problem that you cannot see the data. You cannot see the full picture of the data. You're always going to have like a sample. And that you always try to do the best. It's a very Bayesian approach where I give you the best given the information I have. Obviously, that could be wrong in the reality, but that is the best estimation given the information I have. So yeah, we follow a pure Bayesian approach when we did that.
Sorry, one question here. So in all your slides, you talked about the yearly intervals. So is the data only, the granularity of the data, is it 1 year? Or, for example, the gas spending?
The test. Yeah, it's 2 years worth of data, but it's not the whole transactions. It's just the transaction of the electricity. I mean, only the subset of transaction that we needed in order to compute our insights. That was just for testing, obviously.
Okay.
Can't tell you, we can't really share too much confidential stuff, so I cannot really share information about how it works in production stuff. But this is dev testing, so that's why I'm sharing only those information.
Okay, thanks.
But yeah, this is supposed to work with much bigger data set. Yeah. Any other question?
All right, let's give a hand for our speaker, Gian Mario.
Thank you.
Okay, we'll now break for lunch and be starting back here at 1:50